Okay, hey everybody, this is a video on our electric force and field practice problems. We're going to start with just the multiple choice 1 through 16 because those are the ones that have to do with the electrical force. Number 1, plastic rod is rubbed with a piece of wool. During the process, the plastic rod acquires a negative charge and the wool acquires an equal amount of positive charge. If I have a rod and we have some wool and they're both, say, neutral to start with, this is an example of the triboelectric process of charging something. When you rub those together, just like a balloon on your hair, we have the plastic rod acquiring negative charge. So those negative charges must have come from the wool to the rod. So this gets a charge, say, of -3 on the plastic rod, which means that the deficiency of 3 electrons leaving the wool, means it will have a charge of +3. Positively charged sphere is brought near one end of an uncharged metal bar, so it's neutral. The bar is, the end A and B of the metal bar will become charged negatively over at the A side and positively over at the B side. And this is an example of polarization, which we had a short video about. Don't need to touch that metal bar, just use the positively charged sphere that's brought close to polarize the bar. So it brings the electrons that are free to move inside the metal bar towards the A side. So A becomes, the end A becomes negative, and end B will become positively charged. The whole thing is still neutral, though. A sphere A carries a net positive charge, sphere B is neutral. They're placed near each other on an insulated table, so they don't lose any of their charge to the table. Sphere B is briefly touched with wire that is grounded. Which statement is correct? So let's just think about what's going on right here between sphere A, which isn't touching sphere B, it's just close to it, and sphere B. If it's neutral to start out with, which it is, then it's got a bunch of pluses and minuses, but the minuses are being pulled over to the left side of sphere B because they're attracted to sphere A. The negatives are attracted to the positively charged sphere A. Then when we ground it, that's the grounding line right there, that means it's connected to the Earth, and the Earth is like an infinite reservoir of electrons. It can give you electrons, or the Earth can absorb them, like a lightning rod will absorb the electrons and ground that electrical discharge from the lightning straight down into the ground. So once we ground it, these electrons down in the Earth are going to be able to come up through the ground line because they're going to be attracted to those positive charges on the right side of sphere B. They're essentially being pulled up by this force from the positively charged sphere A. It's pulling all the electrons towards it. So when we ground sphere B, electrons come up from the Earth and into sphere B, and so we get more electrons in there. And then when you disconnect the ground line, so that sphere B is isolated again, now it's become net negative. It has more negative charges in it because it was grounded to the Earth, and sphere A's positive charge is able to pull up electrons from the Earth. So which statement is correct about sphere B? Sphere B is now negatively charged. An originally neutral electroscope is briefly touched with a negatively charged plastic rod. Which statement is correct? You can see this in the video that I did with my electroscope. I had a plastic rod like this. Could be some plastic PVC rod. It's charged up with extra negative charges on it. When it touches the conductive electroscope, some electrons are going to jump onto that electroscope, and the electroscope will become net negative. This isn't like rubbing two things together and you have an equal number of charge leaving one object and going to the other so that one becomes negative and one is positive. This one we already have excess electrons on the plastic rod, which is going to jump to the electroscope, and the electroscope is going to become negatively charged. The rod itself can have a little negative charge left on it, or it could become neutral, but it's not going to become positively charged. Okay, here we have a few questions about a charge capital Q, which is right over there on the left side of the grid. And then we can place another charge at different spots along that grid. So in 5, an electric charge capital Q is placed at the origin. Charge little q is placed at point B. So there's little q. And the force on charge little q due to the charge big Q is F. So this experiences some force F. Let's say it's an attractive force. They're oppositely charged, positive and negative. So maybe that's the force F right there. What is the force on charge little q if little q is moved to point A? So you can see initially at point B it's a distance of 1, 2, 3, 4 units away, and if it's moved to point A then it's 2 units away. Then we can use Coulomb's law to see how the force is going to change. We're changing the distance, that's r, the radial distance. So if we get twice as close, we get closer, r goes down, we're cutting r in half, so that means that our force is going to go up if the value of the radial distance goes down. How much does it decrease by? 1/2. So if it gets twice as close, we're going to get 4 times the force. We'll have 4 times the force because the force electric varies inversely with the square of the distance. So that means if we get twice as close, we get 4 times the force. If we get 3 times closer, we get 9 times the force, because 3 squared is 9. So this one we're going to have 4 times the force, that's going to be A, 4F. An electric charge, capital Q, is placed at the origin, little q is placed at point A. So we change it up, we say, okay, now little q is at point A, there's little q, and experiences a force F. So let's say that's the force it's experiencing. Let's say it's attractive. What's the force on charge little q if little q is moved to point C? Then we move it over here to point C. Well, let's say initially it's a distance of 2 away, and then when we move it, it's a distance of 6 units away. So what happened to our r? R became 3 times larger. We tripled the distance away. So in this case, we're making r a larger value, 3 times as far away. Our force is going to decrease, and it's not going to be 1/3, but now the new electric force, because it varies inversely with the square of that distance, we get 3 times as far away, then we're going to have 1/9 the force that we had initially. So it's going to be D, force F divided by 9. And a student in a physics lab wants to determine the type of electric charge on an initially charged electroscope. An electroscope is already charged up with something. He brings 2 charge rods without touching the electroscope. The positively charged rod causes the leaves to move further apart. The negatively charged rod causes the leaves to move closer to each other. What type of electric charge? Then the electroscope has these leaves on it that are already spread apart because they have the same type of charge down in the leaves. So we could say this electroscope could already be, it's got a bunch of pluses and minuses that are paired up in there, but it's already charged up with something, so maybe it has extra pluses. So it would be net positive. So somehow it lost some electrons earlier because it's already charged up. So if it has extra pluses, then these pluses are going to repel each other and cause the leaves to move apart. Did a video on this showing what the electroscope looks like when we do that. Okay, or it could be negatively charged. Right? They're saying we don't know what the charge of the electroscope is, so the leaves are spread apart. We could have a bunch of pluses and minuses paired up in there, but maybe on this one we have an excess of negatives. Maybe we have extra negatives on it. We don't know, because that would also cause a repulsion of the leaves and they'd spread apart. So we bring the 2 rods close to it and test it out. So the first rod's brought close, and that's a positively charged rod, and it causes the leaves to move further apart. So let's see, if we brought a positively charged rod close to this one, all right, this one has a net negative charge. This one on my left has a net positive charge. If we brought a positively charged rod over here close to the one that's, let's say it's net negative, then that would cause our negatives, our electrons that are free to move around, it would cause them to move up towards the top of the electroscope, meaning that our leaves would then move closer together. Okay, if we brought our positively charged rod towards a already positively charged electroscope, that's going to cause our electrons to move up again towards the top of the electroscope. So we have these negatives that might be down here. They're going to move up, attracted to the positively charged rod, and then that means we're going to have even more plus signs by themselves down there in the leaves, and that's going to cause our leaves to move further apart, repel even more, because there's more positive charge there for them to repel. So bringing our positively charged rod closer to the electroscope, causing it to have its leaves move further apart, we showed down here, that means the thing must have been already positively charged. Okay. 2 charged objects with equal charge of capital Q separated by a distance r attract each other with a certain force. If the charges on both objects are doubled and the separation is halved, the force between them is the same as our Coulomb's law interactive. Here's our Coulomb's law. We have a charge to start off with, Q over R squared. There's our Coulomb's law. And now we have a new electric force. Let's call it Fe prime. And what happened, the charges on both objects are doubled, right? So now we have 2Q and 2Q, and the separation distance is half. So now it's R over 2. So I've got K times now 2Q times 2Q divided by R is cut in half, so I have R over 2 squared. So that means our new electrostatic force, Fe prime, is going to be, let's look at my coefficients. I've got K times 4 times Q squared divided by R squared over 4. You got to remember to square everything. So that means if I clean this up a little bit, I've got 4, just keep all our variables that are in the numerator, divided by R squared divided by 4. So when I have a fraction in denominator, R squared divided by 4, that means it's the same as multiplying the numerator by 4. So this becomes Fe prime is 4 times K times Q squared over R squared. So our new electrostatic force is going to be 16 times KQ squared over R squared. There's our original one, KQ squared over R squared, and now we have 16 times that. So it's 16 times greater. And think we increase the amount of charge, so that increases the force, and we decrease the distance, that also increases the force, so we're increasing the force a lot, specifically 16 times greater. 9. Two identical conducting spheres are charged plus Q and minus 3Q and separated by distance R. That's up here in this picture. The attractive force between the spheres is F. Two spheres are brought in brief contact and then moved to the original positions. The new electrostatic force between the spheres is F prime. That's what this is. Which of the following is true? So to start off, let's say up here, our original force is K times plus Q times minus 3Q divided by R squared. And we could write that one more time as I have K times minus 3Q squared over R squared. I'll write that once more and bring the negative out. The negative is simply going to show us attraction. 90 by 3. Negative shows us attraction. Because they're opposite charges, a positive sign would show us repulsion. Okay, so there's the original electrical force. When we touch them together, look at the total amount of charge that we have to start off with. We have a positive Q, we have a negative 3Q, which means our total amount of charge for the entire system here is going to be minus 2Q. Conservation of charge says we still have to have minus 2Q in total, and when they touch, they're going to balance out. Kind of like pouring cold water into some hot water, the temperature is going to balance out somewhere in between. So if I have a plus Q, maybe I have a bunch of pluses and minuses in here, but we're missing an electron, so this is an extra plus sign in there. And then it's going to touch another sphere that has minus 3Q, so it has an extra 3 minus signs in there. So there's the minus 3Q, and here's the plus 1Q. When they touch, they're conductive. The electrons are going to want to spread out evenly over the whole thing. So what's the result that we get after we touch them and separate them is we'll have those two spheres again, but now we'll see how many electrons are going to want to jump over. One jumps over, and that'll make this a neutral sphere on the left, and this one will become 2, minus 2. This will become 0. And then if we get another one to move over, then this will be negative 1Q, and this one will be negative 1Q. So when we touch them together, the electrons are going to move uniformly, separate and move uniformly over both spheres like they're one giant conductor until everything's balanced out. So each one's going to be a charge of minus 1. Then we separate them back out to this original distance R in the picture. So now they're back at that original distance. So what's the new electrostatic force? F prime is going to be K times minus 1Q times minus 1Q divided by R squared. It's still the same R. Notice that my Minus signs will cancel out, and I'll get a positive, and I'll have k q squared over r squared. So how is that similar or different from our original, that's our f prime, our original one? Well, it's going to be 1/3 the magnitude. This one's 3 times kq squared over r squared, and this one's just a regular 1 kq squared over r squared. So fe prime is 1/3 the strength of the original force we had. So the new electrostatic force, F prime, which of the following is true? F prime is equal to 1/3 the original force, right there. Okay, the next few ones we get some geometry to do as well, and vectors. So here in questions 10 and 11 we have this orientation is an equilateral triangle. So we know what the angles are going to be in there. And then we have these charges at these different spots around our triangle at the vertices. So we've got plus q, another plus q, and another plus q. So they're all repelling each other. They're all repelling. They're all the same distance apart. The distance r, equilateral triangle's got equal length sides. All right. So what is the direction of the net force on charge C due to the other charges? Well, charge B and C, I can look at them by themselves. They're going to repel. And so what is the charge at point C going to feel? It's going to feel a repulsive force in this direction because they're both positively charged. Then we have the charge A and C that we can look at. They're also both positive and they're repelling. So I'm going to have a force this way, equal in magnitude. It's the same amount of charge, same distance away, and that's also going to be repelling charge C. What is the direction of the net force, though? Notice that these have components, just like we did with forces back in October and November. We have components in the x direction, and we have components in the y direction of each of these forces. Now remember, our purple lines here represent the electrostatic force from particles A and B repelling particle C. They're the same magnitude and the same distance away. So these force components in orange that are in the x direction, those are equal in length, so they're going to cancel out. And then I have these components, these vertical components of the force, you could say in the y direction, which are also going to be the same magnitude, and they're both pointing in the same direction, and they don't cancel out, they add up. Okay, so those two components in the vertical or y direction are going to add together and give me a total force that's straight up. That's going to be the net force that particle C feels. 11, what is the magnitude of the net force on C due to the two charges? Now we want to know what the magnitude is. We know the magnitude, the net force, the magnitude, how much the net force is acting on particle C, is going to be the sum of both of these y components. They're adding together and pushing the charge upwards. So it's going to be 2 times Fy, because we got 2 of them. Okay, so we got a 2 in there. Now we just need to know what the force Fy is. So I'm going to have 2 times something else. We got to see how can we express that force. We know we've got Coulomb's law, Fe equals K Q1 times Q2 over R squared. Let's take a look. We have a force here in purple, just looking at one of the forces there. And we have a vertical component in green. We need to figure out what that magnitude is, which means we need to know an angle. So what angle can we know? We can know what this angle is right here. It's going to be the same angle as the angle right down there. Okay, so what's the angle down here in our triangle? It's got to be 60 degrees because it's equilateral. This must also be 60 degrees. So that means that Fy in the vertical direction must be the total force from one of those charged particles pushing particle C away times the cosine, the sine, because we're looking at the opposite side. Here's 60 degrees, there's the opposite side, Fy is what we're looking at, sine of 60 degrees. Alright, so to get our net force, we're multiplying by 2 because we've got 2 of them. So we've got 2 times, what is that force F? That force F is going to come from Coulomb's law. So I've got K times the two charges. So I've got positive Q and another positive Q. So it's going to be positive capital Q squared divided by the distance. That's the radial distance r. So over r squared times the sine of 60 degrees. What's the sine of 60 degrees is going to be square root 3 over 2, or 0.86-ish. Okay, and that gets me the magnitude of the net force. I notice that I have these 2's are going to cancel out, and these two positive Q's up there, capital Q's, those are going to turn into just Q squared. So my final answer is going to be for the net force that I have square root 3 times K times Q squared over R squared. Square root 3 KQ squared over R squared is answer choice A. Geometry, that's fun, huh? All right, 12, 13, 14, we're almost there. We got three charges in corners of an equilateral triangle again, with the side length R. The charges A and C are positive, but B is negative. What is the direction of the net force on charge C due to the charges A and B? So we'll do charge B acting on C. We just look at those real quick. What are they going to do? That's a positive and a negative. They're going to attract. So I'm going to draw on a force vector to indicate that electrostatic force. That's the force from B. Then I have this force from A to look at. That's a positive charge acting on a positive charge, so they're going to repel. It's going to be the same magnitude as my purple arrow because it's the same distance away. They're both the distance r away, and they're also the same magnitude of charge. It's 1q and 1q, just one's positive and one's negative. Okay, so if I want to see what the total net force is acting on that particle C, I know it's going to have components here. A vertical component, that's not the right color, a vertical component for each of these that's going up in one case and down in the other, and those are equal, and they're going to cancel out. And then I have a horizontal component of each one, and those are going to add together. They're also going to be equal because they're the same amount of charge and the same distance away from point C. Okay, so my total amount of force is going to be the sum of both those red lines. There's going to be my net force. For clarity, our orange one here was the force of A acting on C, and our purple one is our force of B attracting, acting on C. And our net force is going to be the sum of these two x components of the force. And then green we had again the y or vertical components of the force, which are canceling out. Okay, so the net force has a direction to the right, and that's answer C. What is the magnitude of the net force charge on C due to charges A and B? We're still looking at our triangle up here. All right, well in this one it's like the previous one. If we want to get our net force, then we need to add up these two red horizontal components. So I have two of them, so I'm going to have 2 times whatever that force is. I can pick one of them. They're both the same amounts of force. My purple and orange are the same magnitude force because it's the same amount of charge and the same distance r away. So it's whatever that force is, but I need the horizontal component. I need the horizontal component there. So this horizontal component I could look at drawing a horizontal line here to help us see where the angle is going to come from. Okay, here's our 60 degrees. Here's our 60 degrees again. So the horizontal component, that means this is also 60 degrees. Look, that horizontal component in red is adjacent to, it's right next to that 60 degree angle. So F in the x direction is going to be my total force times the cosine of 60 degrees. So I have F times now the cosine to get my horizontal portion, cosine 60 degrees. And we'll have 2 of those because we have those 2 charges. So we got the 2 in there. So this becomes 2 times, let's look at our Coulomb's law again. Our electrostatic force for F is going to be K times q and another q over r squared. My q's are, I got a negative q and a positive q and another positive q and a positive q, so it's just the amount of charges, positive q, and the cosine of 60 degrees. Cosine of 60 degrees is going to be 1/2. So right away I can see those 2's are going to cancel out, and the total amount of charge, the total amount of force, the net force is k q squared over r squared. My 2's canceled out. So I can find geometrically with my vectors again, just like in the previous one, the total amount of force. Okay, 4 positive capital Q charges are arranged in the corner of a square as shown in the diagram. What is the direction of the net force on the test charge Q, little q, placed at the center of the square? Again, just look at each of these things individually, like each pair of them individually. A positive Q, we're going to get repulsion there. Positive Q, same distance away, we're going to get repulsion again. And those are going to be equal in magnitude, so they'll cancel out. Same thing for my other points. This is going to be between positive Q and positive Q, a repulsion this way. And then we're also going to have a repulsion this way from the other corner. They're all going to balance out. So the net force is going to be 0. Okay, last 2. 4 capital Q charges are arranged in the corner of a square as shown in the diagram. What is the direction of the net force on the test charge little q placed at the center of the square? Okay, now we've got some attractive and repulsive forces happening. So we'll do, I'm going to call this one purple. Maybe orange. That's not orange. Come on. This one orange. I've got a red one, and I'll have a green one. Okay, so I'll use those color schemes to show each force acting on our plus little q in the middle. So starting from the top right, in purple, we've got a positive q, so we're going to have repulsion this way. Okay, then go into the bottom right. In orange, I've got a positive q and a positive q, and we get repulsion. So I get a force that way. Then I've got a negative q, bottom left, negative q and positive q, we're going to get attraction. So that means I also have another force like that. And then at the top left, negative q and positive q get attraction again. So I have another force vector like that. So I have vertical components for each of these guys that are going to end up balancing out or canceling out vertically. And then we'll have horizontal components. Right, so all the horizontal components are going to add up together, and we're going to have a direction of the total force, which is going to be entirely to the left. That's where the net force is going to act on little q. Okay, so that's answer choice C. Hey, last one. We've got, is it? Yeah. 4 capital Q charges are arranged in the corner of a square shown in the diagram. What is the magnitude? Oh, magnitude. The net force on the test charge, little q, placed at the center of the square. So now we want to know magnitude. How strong is that force? We just showed its direction up there. It's the same setup, but now we want to know exactly how big it is. Okay, so we're just going to take one of these forces, because we know all 4 of these positive q's at the corner, they're all going to exert the same magnitude force on the little q in the middle. Okay, because they're all magnitude 1 charge. They're 1 q, some are positive, 1 negative. Okay, so all we need to do is figure out what is the magnitude of the force from one of those things. So let's say we look at this guy right here, this positive q acting on this positive q. We know we're going to have a force like this. That's going to be the force acting on it. This is just for one interaction. Okay, we need to know this distance, because we need to know how far away they are. So I'm going to call this distance right here h. We'll see why in a second. That's how far away these objects are that are charged. We need to know that, because in order to calculate our force in purple, we need to use our Coulomb's law. K q1 q2 over r squared. Okay, so let's take a look at how we could find that distance. The amount of charge we know, it's positive 1q and positive 1q. Easy. Coulomb's constant K is going to stay the same, but R is actually this distance between the 2 objects right there. And in their diagram, they've called R this, the length of side of the square. So R and H are not equal to each other. H is the distance between the 2 particles. So we need to use that. We need to use that value for H as our radial distance R. So we need to figure out what that is. Not too difficult, because this is a square. So I'm going to use my other color here to just draw a simple triangle. If I make a line here, let me get a different color. Here I have a right-angled triangle inside my square. I know that this angle at the corner of a triangle, that's going to be 90 degrees. And this diagonal that's coming through it is going to cut that into a 45-degree angle, which means this is also a 45-degree angle down there. Which means my hypotenuse right here, h, is going to be the square root of the sum of the squares of the subtending sides. H is a hypotenuse. It's the square root of whatever the value for this length of the triangle is that I've just drawn, squared, plus this length of the triangle squared. But the total length of the side is r. So each side of this triangle in green I just drew is r over 2. So h is the square root of r over 2 squared plus r over 2 squared. I'll work that out real quick. I got the square root of r squared over 4 plus r squared over 4. Or that's going to be the square root of twice r squared over 4, which is the same as r squared over 2. Which then that also means that h squared is r squared over 2. And that's what we're going to want because h is the distance between those two particles, which is our r, and r squared will be h squared. So the force between two of these particles, this plus q up here and this little plus q down there, that force can be expressed, its magnitude, as k times, I got big Q and little q, divided by h squared. And I know what h squared is. I'll put my k upstairs here real quick. H squared is r squared over 2. Okay, and then I have a fraction in my denominator, so I'll clean that up. I got 2k big Q little q over r squared. Okay, whoa, there's the beginning. So that's the force that's represented by this purple arrow down here. That's the force that the little q in the center experiences from any one of the other charges around it. The directions are just different. Okay, so if we want to get the net force, the magnitude of the net force, we need to figure out what the value is for this full blue arrow pointing to the left up there. And that's the combination of all 4 of the horizontal components from each of these 4 charges. So I need to find the horizontal component of this electrical force we just found. So we'll say our net force is going to be 4 times the horizontal component of the electrostatic force. So I say Fe sub x for the x component. That's going to be the magnitude of the net force. So I've got 4 times 2k big Q little q over r squared times the x component. The x component is going to be the part that's just right here. So I'll have like a force, the traction from that one. I have an angle of 45 degrees. So my x component is going to be the full force times the cosine of 45 degrees. Or the sine, it really doesn't matter. Because it's isosceles. So 4 times this all right here is the x component, or horizontal component, of one of the 4 forces acting on plus little q in the center. And so since that's only a representation of one of those 4 forces, I need to multiply it by 4. F net is now, let's see, we'll keep it clean, 4 times 2 k q over r squared. Cosine 45 degrees is square root 2 over 2. Right away I can see that I have my 2's inside canceling out. And so I have a net force, F net, that is going to be 4 square roots of 2 times k big Q little q over r squared. And it's directed entirely to the left. Is that an answer choice? 4 square root 2k q over r squared. There it is. Okay, those are the forced multiple choice questions. That's it for today.